Hi guys, so today we're going to talk about conduction, and it's another way for heat to be transferred always from a hot source to a cold sink. So here, so that slide also comes from your book, um, Johnson and Cutnell. But you see here you have a warm body, so that will be your hot reservoir, and heat can flow through conduction to the cold reservoir. So before that, we were talking about um, convection that will happen with fluid. So in that case, it will be conduction. Conduction happens because of the motion of molecules, right? So the molecules, they are always moving. Okay, so they always have a thermal motion. And remember that um, when they're going to move faster, okay, so they're going to have more kinetic energy, there will be more thermal energy, right? So they are always bumping around molecules and particles. So when you have something hot here, those molecules here are going to jiggle faster, they're going to move faster, they're going to have more energy, okay, kinetic energy, and they're going to pass on that energy to the next molecules here, to the next molecules, to my hand. So once the heat here flowing from hot to cold will reach my hand, those molecules are going to bump into the skin. Okay. So the molecule in the skin, they want to join the party. They want to move, okay, to get that same kinetic energy. And of course, it's going to destroy the skin. So there is a message that will be sent through the neurons to the brain to remove the hand if you are burning yourself. So that conduction here happens because of the motion of the molecules, right? So this is explained because atoms or molecules are vibrating or moving or jiggling faster, so they will pass on that energy to less energetic neighbors. Okay, so if materials conduct heat well, they are called thermal conductors, and otherwise, if they don't conduct heat well, they are called thermal insulators. So obviously, um, metal, okay, are good thermal conductor because they have loosely tied electrons. Okay, so that's why they are also good electrical conductors. So they conduct electricity very well. So those electrons are not tightly bound to the nuclei. So they also, you know, pass on that motion to the next, to the neighbors, right? So they not only the particles are moving and pass on that energy, but also the electrons do that. So that's why metals are good conductors as well. Okay, so for electricity, but also for heat. Okay, so heat, remember, is energy in transfer, energy in transit. So when you have conduction, so heat will flow. So remember, Q, okay, will flow. So energy will flow from a hot reservoir to a cool reservoir. So for example, so if I take that, that's a nice picture here that you have. So let's take an example. If you have a house, okay, so a house, let's say it's winter, so it's going to be warm inside. Maybe it will be maintained at 20 degrees Celsius because you have some heater inside. Okay, so this is your house. And then maybe you have the wall. Okay, so that will be just one side of the room, of the house. Okay, so you have one side of the house here, and maybe you're gonna have the wall here, and here you have some insulator. Okay, so I'm just talking about that side of the house. And here you have the outside. So that will be the sink, the cold sink. That will be the hot source or the hot reservoir, the cool reservoir. And that will be the area A. So heat will flow from inside to outside because in that case, let's say the temperature is 5 degrees Celsius. Okay. So let's say the thickness of this wall here is L. So this is the same thing as that. So you can think here and pause the video that and try to derive an equation for the rate at which the heat is flowing. Okay, so we're going to talk about the rate at which the heat, the energy is moving from the inside to the outside. It's a rate because you divide by the time. So it's how fast the heat is leaving the house. So you can think about that. So first of all, it's going to be proportional to the area. So this is very obvious. Okay, if you have a large side here, more heat will be able to escape. Okay, so it's like it's trying to escape. Now it has more ways, I mean, more path to do so. So it's proportional to the area. And it's also proportional to the gradient of temperature per unit length. Okay, so it means larger is the difference in temperature. Okay, more heat will escape per unit time, and that will be per unit length. Okay, so what does that means? So this equation here was developed by, I think his first name was Joseph. Yeah, his first name was Joseph. He was French. So Joseph Fourier, okay, in 1822. And that equation here, so it's missing just a constant of proportionality, is called the law of heat conduction. So it's going to describe how fast the heat is leaving, going from hot to cool. And this is all because those little molecules, they are moving really fast and they are passing on their kinetic energy to the next one that will pass on the next one and so forth and so on. Okay. So that rate at which the energy is leaving depends on the gradient. So it means that if your heater here, instead of having 20 degrees Celsius, now you put 30 degrees Celsius, okay, you want to be very warm, then you're going to have more heat leaving the house. So the heater will have to work even faster. So you're going to spend more money. Okay. So it's better to keep it at maybe 20 degrees Celsius, depending how sensitive you are. Okay. So larger is the difference in temperature. Faster is the thermal energy, okay, or the heat is going to flow. But it's per unit length. So I will explain why. But it means like this. You can think of that. That will be the gradient of temperature, and that will be the length that the heat has to go through. Okay. So that will be the gradient between hot and cool, and that will be the length that the heat has to travel through. Okay. And you see that for the same length, if you increase the gradient, so for example, here it will be 30 degrees and outside it's going to be 5, or here it's going to be 20, outside it's going to be 0. So for the same length, if you increase, okay, the gradient, okay, so you see that Q over T it's going to increase, right? And kind of makes sense. You can remember that because you see, if you have a slope here, okay, things can go down. But if you increase the slope, it's going to go down faster. So it's very much like if you study a DC circuit. Okay, so you have a voltage here, you have a resistance R, for example. You're going to see that the current, so how fast the charges are moving, depends on the voltage. So the voltage is like a pressure pushing the charges. So here it's the same thing. The gradient, okay, it's very much like a pressure or uh, the same way that the current is proportional to the voltage here, you're going to have that how fast the heat is flowing is proportional to that gradient here, okay, per unit length. Now, what you can do is also, maybe I will talk in the next slide, but just want to introduce it here. You can see here, I don't know if I want to take blue instead here. So if you keep the gradient the same, but you increase the length, so it means you make the wall, for example, larger. Okay, so you keep the gradient the same and the wall is larger. Okay, so now it doesn't like blue. So so instead of having L, you're gonna have 2L for the same gradient. You see that also the heat is gonna move slower. You see? So it's easy to understand here. If you increase the length, okay, it has to flow through. The heat has to flow through. Of course, it's going to be harder, to pass on that energy from molecules to molecules. So the heat here, the rate at which the heat is going to flow, it's going to be smaller. So that rate here is inversely proportional to the length and proportional to the gradient. So before going into more details, here is another example. For example, our skin. So if we have a skin here, and you have an area A, one way, but it's not the most important. One way we have to evacuate the heat so we don't overheat is through conduction. So outside, inside the body, maybe it's 37 degrees, okay? And maybe outside is 10 degrees Celsius. So the heat will flow from inside to outside. Maybe we are overheating, so we are getting heat of the heat to cool down. Okay, so that's another example. Okay, so let's look at the slides here. So that's how fast the heat is flowing depends on the temperature difference. It depends on the area and also, that length here, how much the heat has to travel through. Okay, so that will be your equation there. So let's talk about the unit. No, the unit here, let's see. So you see here, there is a constant of proportionality, K, which is called the thermal conductivity, okay, thermal conductivity. So I don't like to write the equation this way. It's for a better understanding and for solving problems, you want to write it that way. The rate at which the heat is flowing from hot to cold through a material, right? And that material will have a length L, and the area here is A, right? So it has an area A, the length is A. So how fast it's moving is being transferred. It's going to be proportional to the area, okay? And proportional to the gradient per unit length. And here, I don't know if you can see the area here. So this is the area, and this is the area. I mean, you have a nice drawing here. So let's look at the units. Um, so this is Q is in joule. So this is in joule. This is in seconds. Okay. So Q over T is how fast energy is flowing. So the unit is watts. And watts is the same thing as joule per second. Okay, area will be in meters square. That's going to be in degree Celsius. That will be in meters. Okay, so if you isolate K, okay, so K, the unit for K will be joules per second meter degree Celsius. Okay, or watt per meter degree Celsius. Joules over second is watt. So watt per meter degree Celsius. Okay. Now you can see here again, heat will flow from a source to a sink. And interestingly, you see this is coming from your book as well. It makes sense that if you increase the area, so if the area is multiplied by 2, you can see here that the rate at which the heat is flowing is also multiplied by 2. So that's why here it's proportional to the area. That makes sense, right? It also depends on the length. So it's inversely proportional to the length, because let's say this is very hot. If you touch it here, or if you touch there, okay, so for the same, if it's for the same gradient, so this is very hot here and your hand will be cooler. For example, this is 100 degrees Celsius. Here you have 37 degrees. Or here you have 37 degrees. So it means you touch it here or you touch it there. So if you multiply the length by 2, okay, of course it's going to get more time to get to your hand. So the rate will be smaller. So it also, for the same gradient, it will be inversely proportional to the length. Right? Inversely proportional to the length. Even though I like to write it this way. Okay, so how fast energy is flowing is proportional to the area and proportional to the gradient per unit length. Okay, and it also depends on the material. So, K. So, for example, if you look at the thermal conductivity for different material, you see that aluminum is a very good conductor, okay, and it's better than lead. And copper is better than iron. So for the same length, for the same uh, gradient temperature, gradient of temperature, so temperature difference, and for the same length, you see which one will be a better conductor. It will be copper relative to lead. And here you have water, and water is a poor conductor. Okay. Ice is also a poor conductor. Air is a poor conductor. Okay. So air is a very poor conductor. So this is why, for example, if you want to isolate something, you will use styrofoam with a lot of little trap of air here, because air will not let the heat go through easily. In addition to that, you want to make this dead, what it's called, dead air spaces. So that means these spaces here are so small that you cannot have convection. Convection cannot happen. So these are called dead air spaces. Oh, it's written here. Dead air spaces. So let's go back to the first slide. You see, for example, an igloo here has some ice and snow, and this is a very bad conductor. That's why it will keep the heat inside. So the heat will have a hard time to go. And of course, you want to have those walls as thick as possible and have a very large surface area as well. Okay? So, so we have a very good way to regulate our temperature. So this comes from your book, uh, three page 389. Okay, so this comes from your book. It's an interesting example. So you can let's go back to my slide. You can go back to you can stop the video and try to do it. Um, so you have the skin here, and you have the total surface area. Okay, and the total surface area, maybe it's a bad drawing here. So you have the total surface area. So skin is an organ, and the total area is 1.7 meters square. Okay, and of course, some of the heat, but not much, it's gonna be um, leaving the body, yeah, because you don't want to overheat, you want to maintain a constant temperature. It's gonna leave the body here through conduction. Okay, so that's one way for heat to be transferred from hot here to cool. Does it say how cold outside is 34 degrees? So here it's cold. And this is 34. And this is 37 degree. So that's not enough, because imagine you live in a very hot place on earth. It could be like 50 degrees Celsius or 40 degrees Celsius. That will not work, right? It will be the opposite. So the body came up with different ways to cool down, because that will not work when it's 40 degrees outside, obviously. So anyway, so fat. Okay, so it's the fat. You have a layer of fat here. Okay, so you have your layer of fat. And that layer of fat is 0.03 meters. Okay, ta ta ta. In half an hour, so the time is 30 minutes. 1 minute is 60 seconds. Okay, and the thermal conductivity of the body is 0.2 joule per second meter degree Celsius. So you can say the rate at which the heat is leaving the body, it's going to be that constant, okay, times the area. times the gradient per unit length. Okay, so that's going to be Q equals K. It's going to be 0.2 times the area 1.7 times 37 minus 34 divided by the length 0.03, okay, times 1800. It's 1800. So Q, so you can plug that into your calculator. I don't know if I did it right. I'm missing something. The area. No, it's good. It's good. And if you do that, you get 6.1 times 10 to the 4 joules. Okay? But that's not enough because in the previous problem, when we were talking about heat, I don't know which page, 360. So 360, and we were talking about the jogger, the hot jogger. You see that the heat in 30 minutes is 8 times 10 to the 5. So it means that the heat that you need to get rid of after 30 minutes, so the same time, during the same time, if you are doing some jogging here, you need to get rid of that much of heat. And if you use conduction, you are only getting rid of 10 times less. So it can help, but that's not enough. So the body has a different way to do it, to get rid of the heat. Very important here is the sweat. So what's happening here? The body push water on the outside. When water is a liquid, okay? When it goes from liquid to gas, so it's changing state, it needs energy. So it takes that energy, that heat from the body. So the body cools down, okay? So this is called evaporation. So each time you have evaporation, it's a way to cool down. Okay, so the body has a way to push water on the skin here. That water here will evaporate, and to do that, it's taking the heat from the body to turn into gas. So that's a very good way to cool down. A different way is through convection of the blood. So the blood is getting, especially to the hands here or to the feet. Okay, it it's getting, so it's hot. Okay, so it's getting rid of the heat. So now the blood is cooler and it's gonna go over the body. Okay, so the blood is convecting all around. It's taking the heat and then taking that heat to the outside, and then it's cooling down everything else. And then a different way is also through radiation, because we are emitting infrared, and we'll talk about radiation next time. Okay? So that's why there was this nice example for athletes. When athletes are overheating, they can place the hand in something cool, maybe cold water or ice or something like this, to cool down, right, more quickly. Because an athlete has a lot of muscle, so you have a lot of muscle relative to the small area of the skin, so you can overheat because you don't have enough skin to get rid of all that heat. Okay, so that's just a parenthesis. So let's go back to here. Okay, so that here, if you have a gradient, so you have 0 degrees Celsius here, 100 degrees Celsius. That's another problem from your book, but I think there was a typo. So I'm just going to give you a different example here. Let's say you have this, let's say this is a, uh, maybe this is your house. No, this is not a good example. So this part here is at 0 degrees Celsius. This is 100 degrees Celsius, and there is a bar in between. Let's say this is 1 meters. It kind of makes sense that just in the middle here, it's going to be 50 degrees Celsius, right? And for example, here, that will be 25 degrees Celsius. And here it's going to be 75 degrees Celsius. Okay. So it means that if you have the same rate here, okay, because there is no leak, okay, the heat cannot leak out. So Q over T, so the rate at which the heat is flowing is going to be the same all over. Okay, so Q over T is going to be the same, right? And Q over T, okay, is proportional to the um, change in temperature over L. So if you put L here and you have delta T, so you go from 100 Celsius here. Okay, this is 1 meters and this is 0 degrees Celsius. You see, it's a linear relationship. So Q over T here, it's going to be proportional to the slope. So it makes sense that here, okay, if you put at 0.5 meters, here it's going to be at 50 degrees Celsius. So you have this relationship as long as the flow here is going to stay the same because it doesn't leak out anywhere. So there is a conservation of heat from here to there. And you see that delta T over L, so that's going to be 100 degrees minus 0 over 1. It's going to be, for example, delta T1 over L2. So for example, if L2 equals, I don't know, 0.25, okay? So you can find that, I'm going to put a 2 here, delta 2 will be 100 times 0.25, that will be 25 degrees Celsius. So at any place here, you can find the temperature. So you can do experiment like this. You have a bar here. This is hot, you know the temperature. This is cool, you know the temperature. And you see that the temperature is going to decrease, but it's going to be a linear relationship. Okay, so you have a linear relationship between the length of your bar and the gradient. And if you want to learn more, here I have the link where I found this diagram. Okay, what else? So, for example, here, if you are at very close to the end at 0.8 meters, okay, so you want to find out the temperature at that point here. So you're going to say delta T between here and there over L will be delta T2 over L2. Okay, and you will find in that case 80 degrees Celsius. Okay, so there was one problem like that in your book, but we kind of make it more complicated than it was supposed to be. Okay, so there is one problem like this here. There was some typo, but it's the same principle. Okay, so let's move on. Next problem also comes from your book here, so you can pause the video and try to answer. So once you understand how it works, those problems are it's not that hard. Okay, so in that case, here you have the hot reservoir, and this is the cold reservoir. So outside is 4 degrees Celsius. Inside it's going to be 25 degrees Celsius, but you have two layers, right? So in layer one, it's the insulation, and layer two is the outside of the house, so it looks good. And you're gonna have Q over T flowing, okay? And because it's continuous, it doesn't stop anywhere. The Q over T is gonna be the same going through that layer and going through that layer. Okay, so it's going to be the same rate at which the heat is moving. But here you're going to have a temperature T. So see, it's going to go from 25 to this temperature here and that temperature to 4 degrees Celsius. Okay, but the rate at which it's moving is going to be the same. So they want to find out what's going to be Q leaving the house over 1 hour. So first we need to find that temperature here. Okay, so the rate at which it's leaving that layer here, the rate at which it's flowing through that first layer, it's going to be equals to the area. Okay, so the area is 35. So I'm going to put area times the 0.03. That will be the thermal conductivity times the gradient between here and there. So that will be T minus 25. Okay, divided by the length here, the size. So that's going to be 0.076. And you know that Q over T, okay, it's going to be the same heat flowing per unit second through that layer here. The area, it's going to be the same. The conductivity here is larger. Okay, it's not as good as an isolator. Outside is, so it's going to be hot here. I should put 25 minus T, sorry. 25 minus T. And here is going to be T minus 4. And here the layer, the size here, the width is going to be 0.019. So you're going to say those two equations are equal to each other. So you can cross out A, you can solve for T. So it's just algebra. And I don't know if I did it. Yeah, it's just algebra. What you can do, you can distribute. You can distribute and then divide. So you distribute here this and that, and then distribute here and there, and then you divide. So doing so, I got, if you distribute, you're gonna get 0.75 minus 0.03 T over. So of course you want to do it, okay? equals 0.08 t minus 0.32 over 0.019, and you can isolate t. Okay, so you divide here, divide there, divide here, divide there. So you're gonna get 9 minus 87 minus 0.39 t. Okay, so this divided by that equals 4.21 t minus 16.84. Okay, and you can isolate your t. So you get 26.71 equals 4.60, and you get T equals 5.8 degrees Celsius. So it went down from 25 to 5.8 degrees Celsius. So that means, it takes a lot of, the rate is small here, and then it's going to go fast, 5.8 to 4 degrees Celsius. Okay, but you are not done because they are looking for Q. So then you can go back to the first equation. Okay, so you say Q over the time, so 1 hour, so 3600 equals the area, which is 35 times 0.03 times 25 minus t, okay, over 0.076, and t, we have already solved that, is 5.8. Okay, so you can solve for Q. And if you do that, that's going to be 9.5 times 10 to the 5th, or 10 to the 5 joules. Okay, so let's find out. 5.8 degrees Celsius. And you see the steps here. And then you plug everything in and you get the answer. So this is a conceptual question that also comes from your book. So we already talked about a fridge, the way it works. So you have a fluid here circulating inside, and there is convection, but it's called forced convection because by doing work, okay, you're taking the warm from inside the fridge and dump it outside. So it's like you are forcing heat to move from cold reservoir to hot reservoir. Okay, and that will happen only if you are doing work, right? So that fluid here circulating will collect the heat from inside the fridge and will dump it outside because there is a motor that will do work, right? To achieve that. But here you have an exchange here, okay, between, so you have a tube with the fluid and it's inside that plate, okay? And so the heat from inside the fridge will go through that plate here, through a layer, okay? And it's made of aluminum. That plate here is made of aluminum. So is it better to use aluminum of steel? I don't know what you think. But if you look at the thermal conductivities of different materials, okay, if you go back to this slide here, you see that aluminum is a very good conductor and steel not so much. Okay, so you don't want to use steel, you want to use aluminum. In addition to that, um, that plate here can be coated with ice. So it's a good idea to remove the ice because you see here you increase, not only you increase the length for which the heat has to go through, but ice is not a good conductor. So you're making things work and the motor has to work harder and you will have to pay a higher bill. So that's a nice example that comes from the book, comes from the book as well. Another example from your book, uh, which also is very interesting, is, okay, sometimes the farmers, when the temperature goes beyond, I mean, below freezing, they will spray strawberries with water because water, okay, will freeze, so it will turn to ice. So two things will happen. So first of all, relevant to this unit, the ice will be like a layer, okay, that will protect the strawberry because heat cannot flow easily from the strawberry to the outside, freezing. Okay. Here you can survive -3 degrees Celsius, for example. These are strawberries. Okay. So that's one application. The other thing is when you are spraying water here, the water will turn into ice. But that will happen when that happens, when water turns into ice, it will release energy. Okay. It will change the state. Okay. It goes from a liquid to a solid. By doing so, it's going to release energy, and that energy will warm up the strawberries. So actually, that will be the best explanation. So of course, ice is a good insulator, but also when the water goes to ice, it will release energy. Okay, and by releasing energy, it's gonna warm up the strawberries. Okay, so that will be it for this.